Hello friends. So welcome to lecture series on non-linear programming. In the last lecture we have seen what geometric programming problems are. We have seen that there are some complicated non-linear problems which may be non-convex and how to solve such type of problems using arithmetic geometric mean inequality. Now in that lecture we have seen only unconstrained polynomials optimization. I mean, if we have a problem of polynomials without any constraint, then how can we use arithmetic geometric inequality to solve those type of problems. Now in this lecture we will see that if we have a constraint problem, constrained polynomial optimization with equality constraint, we are focusing only on equality constraint in this lecture, then how can we solve such type of problems. So let us see. So what is the formulation? Where we have a geometric programming problem with equality constraints. So consider the case of minimizing an objective function which is the sum of polynomials subject to the equality constraints, okay. That is minimization of fx subject to gix is equals to summation r running from 1 to pi cir and uir x I running from 1 to n, where pi denotes the number of terms in the ith constraints, okay, and uir is the same as the polynomial term, okay. Now let us discuss the same thing again. Now we already know that sum of capital Ui's where I running from 1 to n is greater or equals to product I running from 1 to n ui upon delta I whole raised to power delta I. So this we have discussed in the last class. This we obtained from the arithmetic geometric mean inequality, okay. So where sum of delta is 1 and all delta I are greater than 0. Now if sum of delta is not 1, suppose it is some lambda. So how can we apply this inequality there, okay. So suppose, let us suppose sum of delta I is some lambda. If sum of lambda delta I is some lambda, so of course we can't apply this inequality as such because this is valid only when sum of delta is 1. So how can we apply this inequality? We divide each delta I by lambda to make the sum equal to 1. So what we do basically, we write delta 1 upon lambda plus delta 2 upon lambda and so on delta n upon lambda is equals to 1. So that means to apply this inequality for this type of problems, we replace delta I by delta I upon lambda, because now the new delta I is a delta is upon lambda whose sum is 1, okay. Because sum of these delta, now this is one delta, this is second delta, this is third delta and another delta and sum of this is 1 and it is applicable only when the sum of delta is 1. So that means to apply this inequality for this problem, we replace delta I by delta I upon lambda, okay. So what we obtain, it is summation I running from 1 to n ui greater than equals to product I running from 1 to n ui upon delta I by lambda whole raised to power delta I upon lambda. This inequality for which system? This inequality holds when sum of delta is lambda, okay. Now what is the right hand side? Let us see. You can simplify first. It is lambda delta 1 u1 whole raised to power delta 1 upon lambda. The second term is lambda delta 2 u2 whole raised to power delta 2 upon lambda, and the nth term is lambda delta n un whole raised to power delta n upon lambda, okay. This is the right hand side. Now you first raised whole raised to power lambda both the side. So, this will implies summation I running from 1 to n ui whole raised to power lambda in the left hand side. When you do this, so it is, and you collect the powers of lambda, okay, it is lambda raised to power. From here when you take this lambda to the right left hand side and collect the powers of lambda from each term, so it is lambda raised to power delta 1, lambda raised to power delta 2, so it will add up, and the remaining term will be u1 upon delta 1 whole raised to power delta 1, u2 upon delta 2 whole raised to power delta 2, and so on un upon delta n whole raised to power delta n. So, this sum is again lambda from this expression. We are solving this expression for this sum of delta is lambda. Okay. So, this is equals to lambda raised to power lambda, and this is product I running from 1 to n ui upon delta I whole raised to power delta I. So, we have obtained another inequality, that is if u1 plus u2 and so on up to un whole raised to power lambda is always greater than or equal to lambda raised to power lambda product of ui upon delta I whole raised to power delta I, where sum of delta I is lambda. Okay. So, we will use this inequality for solving GP problem or geometric programming problem with equality type constraints. How we will do that? Let us see. Let us discuss this by an example. Okay. So, to illustrate how can we solve such type of problem using inequality constraint, let us discuss it by an example. Suppose we have this example, it is minimizing of f which is equals to 40 x1 raised to power minus 1, x2 raised to power minus 1, x3 raised to power minus 1 plus 40 x1 x3 subject to, you divide it by 8, this constraint you divide it by 8. So, what we obtain? It is 1 by 2 x1 x2 plus 1 by 4 x2 x3 is equal to 1, and x1 x2 x3 are strictly greater than 0. Okay. So, first let us focus on the objective. Objective is f equal to 40 x1 raised to power minus 1, x2 raised to power minus 1, x3 raised to power minus 1 plus 40 x1 x3. Now, it is equals to u1 plus u2. Okay. Let us suppose the first term is u1, the second term is u2. So, it is greater than or equals to, by the same inequality, u1 upon delta 1 whole raised to power delta 1, u2 upon delta 2 whole raised to power delta 2, where delta 1 plus delta 2 is 1 and delta 1 delta 2 are strictly greater than 0. This is by the objective function. Now, come to the constraint. What is the constraint we are having? It is 1 by 2 x1 x2 plus 1 by 4 x2 x3 is equal to 1. So, it is u3, suppose it is u3, suppose it is u4 is equals to 1, where u3 is the first term of the constraint and u4 is the second term of the constraint. Okay. Now, to deal with this equation, we discuss it like this, this 1 is always equals to 1 raised to power lambda for any lambda. Okay. So, this 1 can be replaced by u3 plus u4 is upon lambda, because u3 plus u4 is 1. So, this 1 can be replaced by u3 plus u4, and we just now discussed in the slides also that sum of ui's whole raised to power lambda is always greater than or equals to lambda raised to power lambda into product of ui upon delta I whole raised to power delta I, where sum of delta I is lambda. So, this is u3 plus u4 whole raised to power lambda. So, it will be greater than or equals to lambda raised to power lambda into u3 upon delta 3 whole raised to power delta 3, u4 upon delta 4 whole raised to power delta 4, where delta 3 plus delta 4 is lambda and delta 3 delta 4 is are strictly greater than 0. This is by this inequality. Okay. So, what we obtain from here? By the constraint we obtain this inequality. Now, this we can use it here. You see, this we can always write this into 1, okay, and this 1 is 1 is greater than equal to this inequality. So, this is greater than equals to u1 upon delta 1 whole raised to power delta 1, u2 upon delta 2 whole raised to power delta 2 into 1, and 1 is greater than equals to lambda raised to power lambda, u3 upon delta 3 whole raised to power delta 3, and u4 upon delta 4 whole raised to power delta 4, where delta 3 plus delta 4 is lambda and delta 3 delta 4 are strictly greater than 0. Okay. So, it is equals to lambda raised to power lambda, this can be put it outside the brackets. Okay. What is u1? U is the first term of the objective function, that is 40 x1 raised to power minus 1, x2 raised to power minus 1, x3 raised to power minus 1 upon delta 1 whole raised to power delta 1. What is u2? u2 is 40 x1 x3 upon delta 2 whole raised to power delta 2. What is u3? u3 is the third term, first term of the constraint x1 x2 upon delta 3 whole raised to power delta 3, and u4 is 1 by 4 x2 x3 upon delta 4 whole raised to power delta 4. Okay. Now, again you will collect the powers of the variables. Here we are having 3 variables x1, x2 and x3, x1, x2 and x3. You collect the powers of x1, x2 and x3, put it equal to 0, and also delta 1 plus delta 2 equal to 1, apply this condition and try to find out the maximum value of the right hand side. So, what are the equations we will obtain? From this we can obtain, if you collect the powers of x1, it is minus delta 1 minus delta from 1 from here plus delta 2 plus delta 3 equal to 0, delta 1 plus delta 2 plus delta 3 equal to 0. From second term, that is the power of x2, it is minus delta 1, no x2 is here, so no power of delta 2 for x2, and it is delta 3 plus delta 4, that is minus delta 1 plus delta 2 plus delta 4 is equal to 0. Okay. And the power of x3, x3 is minus delta 1 plus delta 2, minus delta 1 plus delta 2, power of x3 plus delta 2 plus delta 4. Power of x1 is minus delta 1 plus delta 2 plus delta 3 equal to 0, minus delta 1 plus delta 3 plus delta 4 equal to 0. Power of x2 is minus delta 1 and plus delta 3, okay, plus delta 3 plus delta 4 equal to 0, and delta 1 plus delta 2 equal to 1, and delta 3 plus delta 4 is lambda. So, here we are having 4 equations, 4 unknowns. Okay. We can solve it and find the values of delta 1, delta 2 and delta 3 and delta 4 of course. Okay. Okay. So, how to now when we solve this equation, what are the values of delta 1, delta 2, delta 3, delta 4 we can obtain. So, you can solve it. I know the values of delta 1, delta 2, delta 3 for this system. For this system, delta 1 can be obtained as 2 by 3 and delta 1 equal to delta 2 equal to delta 3 are 1 by 3. You can solve it and find these values of delta 1, delta 2, delta 3 and delta 4. Okay. You can simply verify that these are satisfying all the constraints, all the equations. Okay. So, what will be lambda? Lambda is nothing but delta 3 plus delta 4, which is okay, and okay, delta 2 plus delta 3 and delta 4. You can easily verify. Okay. Now, delta 3 plus delta 4 is 1 by 3 plus 1 by 3, that is 2 by 3. So, in this way we can find out the values of deltas and lambda. Now, how can you find out the value of the unknowns, that is x1, x2 and x3. Okay. So, for that we will again apply the equality condition. From the equality condition we obtain the equality hold if u1 upon delta 1 equal to u2 upon delta 2 for the first one, and u3 upon delta 3 is equal to u4 upon delta 4 for the constraint. For the constraint also the equality will hold when this condition holds, we can easily verify. Now, from here we can obtain u1 is 40 x1 raised to power minus 1, x2 raised to power minus 1, x3 raised to power minus 1 upon delta 1 is 2 by 3, u2 is 40 x1 x3 upon delta 2, which is 1 by 3, and from u3 is 1 by 2 x1 x2 upon delta 3 is 1 by 3, which is equal to 1 by 4 x2 x3 upon delta 4 is 1 by 3. Also you can easily see that if you have u3 plus delta 3 is equals to u4 upon delta 4. So, this is also equal to u3 plus u4 upon delta 3 plus delta 4, okay, because these are the ratios, and u3 plus u4 is 1, u3 plus u4 is 1. So, it is 1, and delta 3 plus delta 4 is lambda, and lambda is 2 by 3. So, it is 2 by 3. So, it is 3 by 2. So, we can say that it is equal to 3 by 2. So, using these equations, you can easily find the values of x1, x2 and x3. That will be the optimal solution of this problem. Okay. So, in this way we can find out the optimal solution of a such type of problem with equality constraint. Okay. Now, let us discuss degree of difficulty. Now, let m be the total number of terms in fx, fx is the objective function, and all gix. So, including a term of fx and including a term in all gix, we are calling it small m, okay, and n be the total number of variables. Then the degree of difficulty d is given by m minus n minus 1. For example, for this problem how many terms are there? 1, 2, 3, 4, including all terms in the GIs. Here only one constraint. So, 1, 2, 3, 4. So, m is 4. How many variables we are having? 3. So, n is 3. So, degree of difficulty will be 4 minus 3 minus 1, that is 0. So, degree of difficulty is 0 for this problem. That is why we are obtaining a unique solution for delta i's. Okay. If degree of difficulty is less than 0, so GP is not applicable for those type of problems. Okay. Now, if you consider these problems, suppose the first problem. Now, in the first problem, how many terms we are having? 1, 2, 3, 4, 4 terms. So, m is 4. How many variables, how many unknowns we are having? 3, x1, x2, x3, 3 unknowns. So, m is 4, n is 3. So, degree of difficulty will be 4 minus 3 minus 1 by this expression, that is 0. Okay. Again, in this we are having 3 terms 1, 2, 3. How many unknowns? 2 unknowns, 3 minus 2 minus 1, that is degree of difficulty is 0. For this problem, degree of difficulty is, because we are having 3 terms with 1 unknown. So, 3 minus 1 minus 1, that is 1. So, degree of difficulty for this is 1. Now, it is easy, easy if your degree of difficulty is 0, because in that case we are having a unique solution if exists. Okay. So, the right hand side of the inequality will be having a fixed value. Now, if the degree of difficulty is more than or equal to 1, then how can we solve such type of problems? So, for illustration, let us discuss this problem. We already know that degree of difficulty is, this is 1, because it is having 1 unknown with 3 terms. So, 3 minus 1 minus 1, that is 1. So, for this problem, it is again an unconstrained problem. This is simply illustration, that u1 plus u2 plus u3 is greater than equals to u1 upon delta 1 whole raised to power delta 1, u2 upon delta 2 whole raised to power delta 2, and u3 upon delta 3 whole raised to power delta 3, where sum of delta is 1 and delta I is greater than 0 for all I. Now, when you consider the power of x, here only one variable is there. So, how many equation we obtain? Only one, and the second constraint is this, and how many unknowns? 3 unknowns, delta 1, delta 2, delta 3. Okay. So, what will be the equation? It is when you substitute it here, it is x square upon delta 1 whole raised to power delta 1, it is x upon delta 2 whole raised to power delta 2, it is 3 upon x delta 3 whole raised to power delta 3. So, when you collect the power of x, put it equal to 0, we obtain 2 delta 1 plus delta 2 plus delta 3 minus delta 3 equal to 0. So, here we are having only two equations with 3 unknowns. So, it will be having infinitely many solutions. So, how can we solve such problems? Now, what is our right hand side? Our right hand side, when we make it free from x, it is 1 upon delta 1 whole raised to power delta 1, 1 upon delta 2 whole raised to power delta 2, and 3 upon delta 3 whole raised to power delta 3. We want to find out the maximum value of this expression. Okay, we want to find out the maximum value. Maximum value will give the minimum value of f. Okay. Now, what we will do? We will try to express all the variables in terms of one variable, say delta 3. Okay, we will try to express that, we can easily do. You see, delta 1 plus delta 2 plus delta 3 is 1, and delta 2 delta 1 plus delta 2 minus delta 3 is equals to 0. Okay. So, you can subtract these two equations. So, it is minus delta 1 plus 2 delta 3 is equals to 1. So, delta 3, so delta 1 will be nothing but 2 delta 3 minus 1. So, that is in terms of delta 3. So, you can substitute this delta 3 over here or in any one of the equation, when you substitute it over here, suppose. So, delta 1 is 2 delta 3 minus 1 plus delta 2 plus delta 3 is equals to 1. So, delta 2 we obtain as 2 minus delta 3, 2 minus 3 delta 3. Okay. It is delta 2 and it is 1 2 minus delta 3. Okay. So, we have expressed all the variables in terms of one variable, that is delta 3. Now, you can put it over here. Now, you focus only on this term. Okay. What is this term? Say it is g delta. G delta is the right hand side. 1 upon delta 1. Delta 1 is 2 delta 3 minus 1 whole raised to power 2 delta 3 minus 1. Okay. And delta 2 is 1 upon 2 minus 3 delta 3 and whole raised to power 2 minus 3 delta 3. And delta 3 remain as it is. Okay. So, in this way we have expressed the right hand side only in terms of one variable. Now, what we have to do? We have to find out the maximum value of this expression, which is of only one variable. How we can do that? You just take the logarithm both the side, you just take the log both the sides, find out the first derivative with respect to delta 3, put it equal to 0, that will give the maximum value of g delta, for which you can find out the value of delta 3 for which g delta is maximum. Once you find the value of delta 3 for which g delta is maximum, you can substitute delta 3 over here and you can find out the value of delta 1 and delta 2. And once you can find out the value of delta 1 and delta 2, then you can easily say that this equality will hold when all are equal, that is u 1 upon delta 1 is equals to u 2 upon delta 2 equal to u 3 upon delta 3. And that using that you can easily solve, you can easily find out the value of x for which this f is minimum. Okay. So, in order to find out the maximum value of this, you simply take log both the sides, differentiate with respect to delta 3, put it equal to 0, the first derivative, and you can find out the value of delta 3 for which g delta is maximum. You can substitute that delta 3 over here to find out the value of delta 1, delta 2, and that will give the values of delta 1, delta 2 and delta 3. To find out the maximum value of minimum value of f, you use the equality condition. Okay. So, in this way we can solve the problems with constraint polynomial optimization with equality constraint, or if we have a problem having degree of difficulty more than 0. So, thank you very much.